The more the merrier. Let's look at probability with more than one variable. So given a finite sample space S, a set of numbers P1 to PR, that is a probability distribution on S if the sum of the P's is 1, the P's are non-negative, and if A and B are subsets of S and they are disjoint, their intersection is the empty set, then the probability of A union B is the probability of A plus the probability of B. We tend to order the set using the index. In other words, the elements are listed in the order that they're indexed. Variable x is associated with S, which means x is t sub x for some index x. And there may be more than one variable, often an x and a y associated with a set S. Or more rigorously, given S is equal to T1 to Tx to Tr, we can define a new space, a product space, of tuples, T sub x, T sub y pairs for x and y equals 1 to R. And that would be a subset of R squared. For example, a pair of dice rolled simultaneously, x is the outcome of the first and y is the outcome of the second. Another example, two players are dealt cards from the same deck, each play a card simultaneously. X is the value of the first player's card, y is the value of the second player's card. Or perhaps we have S is equal to pairs where x is 1 to R and y is 1 to Q. In other words, their capital X and capital Y are variables associated with S, the first and second components of the pairs that make up S. A trial or instance of xy is of the form T sub x, U sub y pair. For example, a square on a chessboard is chosen at random from row X and column Y. So a trial would be a random choice of capital X and capital Y. A 6-sided die and an 8-sided die are rolled simultaneously. X, Y are outcomes of the dice respectively. So we require sample spaces be numerical so that they are subsets of a vector space, Rn. And the tags are vectors in Rn. And if we have a non-numerical space, we tag it with numerical vectors. So notationally, we have some sample space, S, a subset of Rn. Outcomes are associated with variables, capital X1 to capital Xn in Rn. A trial is a lowercase x1 to xn, where each lowercase xi is an instance of the variable capital Xi. For example, suppose we have a subset of R2 given by the T sub x, U sub y pairs, where x and y lowercase go from 1 to RQ. Then the probability that capital X is T sub x and capital Y is U sub y, that's the probability that we get an outcome with tag T sub x, U sub y. Now very often, we just identify outcomes by indices. So the probability that x is x, y is y, is the joint probability distribution of capital XY. And we often write it P of xy in function notation, the probability that capital X is the index x and capital Y is the index y. In other words, the P of xy function notation is the probability that xy is the outcome tagged by lowercase xy, the tx-uy pair. So, joint probability is the probability that in the trial of capital XY, we get T sub lowercase x, U sub lowercase y. We say the marginal probability of x is the probability that x has outcome T sub x, given that y can take any value, denoted by P sub capital X of x. Now, if we look at these two sets, E sub x and E sub y, you'll notice that in E sub x, it's always the same T sub x, and E sub y, it's always the same U sub y. So the marginal probability, the probability that capital XY is in E sub x, and the marginal probability of y is the probability that capital XY is in E sub y, well, we can calculate those. So the marginal probability with respect to x is the sum over all the possible values of y, u1 to uq. And likewise, the marginal probability of y is the sum over all the x's of p of xy. Now, very often we use a little better notation. So if capital Y is equal to index y, then that's the same as saying capital Y is the outcome u indexed by lowercase y. And notice that allows us to write this sum with the index y equals 1 to q. And likewise, saying that capital X takes on the instance lowercase x means that capital X is essentially t sub x, the outcome indexed by lowercase x. And that allows us to write the marginal probability of y in this way. And we often just let the index variable indicate the margin probability. So rather than subscript capital X and subscript capital Y, we often just write P of X. That means the marginal with respect to X. We let the notation of the variable in the function tell us which marginal distribution we're looking at. For example, joint probability. Dr. Yu in China and I in the USA both flip fair coins at the exact same time. Capital X is my outcome, capital Y is U's outcome. Could be tails, tails, heads, tails, tails, heads, or heads, heads. In other words, our sample space tagged by pairs in R2 is 0, 0, 1, 0, 0, 1, 1, 1, or zeros for tails and ones for heads. Each of these is equally likely, so probability of fourth for each. So my joint probability distribution is actually a constant function equal to 1/4 for all xy. So if I had a trial where capital X was heads and capital Y was tails, well, each outcome is equally likely, so the probability that capital XY is heads tails is 1/4. But using function notation and tagging these events, I would write this as P of 1, 0 heads tails is equal to 1/4. Heads corresponds to 1, tails corresponds to 0. So let's look at the marginal probabilities. So let's look at the probability that I get a heads. That means P sub capital X of 1. Well, that is the joint probability that I get a heads, U gets a tails, plus the joint probability that I get a heads and U gets a heads also. That's a fourth plus a fourth, and that's a half. Probability of heads for me. What about Dr. U getting a tails? Well, that's the probability that I get tails and U gets tails, and plus the probability that I get heads and U gets tails. Again, 1/4 plus 1/4 is a half. Probability of tails for U. If careful, we can use P of X and P of Y without the subscripts. So P of X is equal to 1/2 is the probability that X is T sub X for me. And P of Y equals 1/2 is the probability that Y is U sub Y for U. So joint probability, P of xy is the probability that x is x and y is y in the same trial. If A is a subset, then we're really looking at all these pairs with these possible indices. So sigma here is a permutation of 1 to r, and rho is a permutation of 1 to q. Notationally, saying xy is in A is going to be the same as saying t sub x and u sub y is in A. And look how this is going to simplify our notation. The probability of A is the probability of capital XY in A, and that's just the sum, using our new notation, of the pairs little xy in A of P of xy. So all the usual concepts are available for sets. The probability of A intersect B is the sum over little xy pairs in A intersect B of the joint probability, similarly with the union. B prime is a set of all outcomes in S that are not in B, and we get the very important concept that the probability of B prime is 1 minus the probability of B. And we very often get probability distributions from the data. This is called an empirical distribution. So suppose 1,000 students were asked to choose their favorite college sport. Now this is for illustration only. So here's the raw data, the counts, male and female, and each of them chooses football, basketball, baseball for men, softball for females, or other. We divide each count by the total number of students to get a probability distribution. So there's our probability distribution. It's a joint distribution. So our X is for gender, male or female. Little x equals 0 for male, little x equals 1 for female. And our Y is for sport. So little y goes from 0, 1, 2, up to 3. Suppose a student is selected at random from the 1,000 surveyed. The probability that a student is a male with a favorite of basketball, so that's going to be the function notation P of 0, 1. And we can see that's 15%. The probability that the student is female with a favorite of softball, well, that's P, function notation 1, 2, and we can see that's 20%. Now, what about the marginals? Well, notice first that if we take the males and add up the probabilities over y's, we get 50%. And for the females, we get 50%. So the marginal in X, remember X here is gender, is 50-50. We're equally likely to get a male or a female. The marginals for Y are given by the sums of the columns. So we get 35% that the student will choose football, independent of whether they're male or female. So the event A of male and favorite is not other. Well, not other means football, basketball, or base or softball. The probability of A in function notation is P of 0, 0 plus P of 0, 1 plus P of 0, 2. And that adds up to 45%. The event B that favorite is not football, well, that's everything except football. And notice the probability of B I can get by looking at the marginal. They have to sum up to 1. I can subtract the 35%, and I get 65% that the favorite is not football. So let's look at conditional probability in terms of joint probabilities. So first off, E sub y is where we have fixed y outcomes of U sub y, a condition that y is U sub y. And putting that into our definition of conditional probability, we can let B equal E sub y, and that means the probability of B is the probability of E sub y is the probability that y is U sub y, and that's the marginal distribution in y. If we let A be equal to E sub x, fixed outcome T sub x for x, then A intersect E sub y is just the single outcome T sub x U sub y. So that means that in the numerator, we have the joint probability. The denominator is the marginal probability. And that gives us conditional probability in terms of the capital XY being the little x, little y indexed pairs. And here it is. So let's look at an example. Suppose we wanted the probability that capital X is female, given that capital Y is football. In function notation, that's the probability that X is 1, given that Y is 0. And given this is our definition, notice that P of 1, 0 is there in purple, and the marginal is there in the blue. And therefore, we get 10% over 35%, which is 2/7, which is about 28.6%. Now, what about the probability that X is male, given that Y is other? Well, this is the probability that X is 0, given that we know that capital Y is 3. So the function notation, with our definition, we get that. We're looking at this column at the end, and notice that's 0.05 over 0.05, and that's 1, because notice that female and other was 0. Now, what about the event A that male and favorite is not other? Well, that's that event up there. male and favorite, not other. That's the football, basketball, base, or softball. Suppose event B is favorite is not football. Well, that's everything except football. So the probability of A given B is the probability of male and favorite is not other, given that, conditioned upon favorite not being football. And that is the probability of A intersect B, which is the shaded basketball, baseball for male, the probability of B, which comes from the marginal row, and we get 4/13, which is about 30.7%. So independent variables, let's look at this special case where capital X, capital Y are both associated with the same set S of numbers. Joint probability, P of x, y in function notation, is the probability that x is t sub x and y is t sub y. Now, to define independence, we're going to use the following definition. If the conditional probability, P of x, given that y holds, is equal to the marginal distribution in x for all x, y, and s, then the variable x is said to be independent of the variable y. Notice that if we have P of x given y, the definition, and it's equal to the marginal, then we end up with the joint probability distribution is P of x, P of y, the product of the marginal distributions for all x, y, and s. So therefore, x independent of y means y is independent of x, and variables associated with s are called independent if x sub I is independent of x sub j for all I not equal to j. So in summary, if we have multiple variables, we're looking at a finite subset of Rn. Outcomes are associated with variables, capital X1 to capital Xn and Rn, indexed by lowercase x1 to xn, or samples, or they could be called trials. And an important example we looked at in R squared, and we defined the joint probability of an outcome with tag t sub x u sub y, written as P of xy is the probability that x is t sub x, but that's x is indexed by x, and y is indexed by y. And that led us to another way of understanding conditional probability, which is the probability distribution for x given the condition that y is constrained to be u sub y. So final note, we had an important result. If capital X1 to Xn are variables associated with S, they're said to be independent if they are pairwise independent. This is very important in sampling. It's also important in modeling because the probability jointly that capital X1 is little x1, capital X2 is little x2, so on and so forth, is equal to the product of the individual or marginal probabilities. In function notation, the probability of x1 to xr is the product of the individual probabilities, the marginal probabilities.